If you take a look at the picture on the screen, you will find that a particular device has been shown. Now this device is known as a generator. The function of a generator is to provide electricity and current during the time of load sheddings and power cuts. Now this device works on the principle that whenever there is a change in magnetic flux linked with a coil, a current is generated. So let us find out how this device works and how it helps us during times of load sheddings and power cuts. We have found what direct current means. We studied about the DC motor and we saw that direct current is current where there was a constant flow of electrons in one particular direction. And not only that, the current that flowed through the given conductor was of constant magnitude. So direct current possesses two properties. One, it flows in a particular direction, and two, it is of constant magnitude. Now in contrast to this, we have alternating current. Now how is alternating current different from direct current? In alternating current, the electric charges move in one direction for a short time, and immediately after that they start flowing in the reverse direction. So as you can see from the animation, current is in one particular direction for a brief period of time, and the very next moment current reverses its direction. So this happens over a period of time, over and over again, and this is how we get alternating current. Now in alternating current, not only is the direction changing periodically, it is also the magnitude that keeps changing with time, and this is why the current is known as alternating current. So let us take a look at how a generator functions. As you can see that there is a coil ABCD, and at the one end of the coil there is a particular handle. Now once this handle is rotated, we find that current starts flowing in the coil, as has been denoted by the galvanometer. Now let us study in details about how when we rotate the coil, current flows, and how exactly it flows in the external circuit that is connected with the galvanometer. Firstly, we shall look at the arrangement of the generator, or in other words, how the different parts of a generator are constructed. So firstly, over here, we have what is known as a field magnet. Now the field magnet is usually a permanent magnet which is very, very strong. Now as you can see, within the field magnet, or in other words, within the poles of the field magnet, we have placed the armature coil ABCD. This armature coil is usually wound around a soft iron core. Now two ends of this coil, A and D, are drawn, and one end is connected to slip ring S1 and the other end is connected to slip ring S2. As you can see, much unlike what we had seen in the case of DC motor where there was one split ring, in this case there are two slip rings S1 and S2. Slip ring S1 is touched against brush B1 and slip ring S2 is touched against brush B2. These brushes are carbon brushes across which the external circuit is constructed, or in other words, across brushes B1 and B2 the load is connected. So this is the basic arrangement and the basic structure of a generator. So now let us see how it functions. Initially we have kept the generator at this particular position that you can see. Now we have studied that whenever there is a magnetic flux linked with a coil, an EMF will be induced only then when there is a change in magnetic flux linked with the coil. So in this case, let us count the number of magnetic field lines linked with the coil. It is 1, 2, 3, 4, 5, 6. Now can you tell me, are the magnetic field lines increasing in number or decreasing? The answer is they are neither increasing nor decreasing. They remain constant. So when there is no change in magnetic field lines through the coil, or in other words, when there is no change of magnetic flux, it means no EMF will be induced. Thus we find, since the rate of change of magnetic flux is 0, no EMF is induced and hence no current flows. Now let's see what happens if we rotate the coil in the clockwise direction. So with the help of the handle, the coil is rotated in the clockwise direction. So over here, as you can clearly see, there has been a change in the number of magnetic field lines or the magnetic flux linked with the coil. Over here, the white lines indicate the ones that are not going through the coil, and the black lines indicate the magnetic field lines going through the coil. So as you can see, 1, 2, 3, 4. 4 magnetic field lines are passing through the coil in place of 6 that were initially passing. So what does this mean? This means that there has been a reduction in the magnetic flux. So the magnetic flux associated with the coil has decreased. Due to this, an EMF is induced because this decrease has taken place at a certain rate. So since there is a rate of change of magnetic flux, EMF is induced and current flows through the conductor. Now this current flow can be obtained with the help of Fleming's right hand rule. So I place my forefinger in the direction of the magnetic field, that is this direction, and I place my thumb in the direction of the force. So let's consider conductor AB. Conductor AB, on AB the force is acting in the upward direction because the coil is rotating in the clockwise direction. So the force is in this direction. Now if I stretch out my middle finger, it will give me the direction of current. So as you can see, my middle finger gives me the direction of current along AB, and it is in this direction. Similarly, if I consider arm CD and apply Fleming's right hand rule, I place my forefinger and I place my thumb in the direction of the force on CD, which is in the downward direction because the coil is rotating clockwise. Now if I stretch out my middle finger, I will find that it gives me the direction of current in this particular direction. As you can see, it gives me the direction over here. Now current is flowing along ABCD. So when current flows along ABCD, notice what happens in the external circuit. Current flows along CD, comes all the way to slip ring S2, and then since it is connected to carbon brush B2, it flows in this direction, as you can see from the deflection of the galvanometer, and it flows in this direction, reaches brush B1 and all the way along AB. So this is how the current is flowing. So the coil is rotated in the clockwise direction, and a point comes when the armature coil becomes parallel to the magnetic field lines. Now as you can see from the initial position where all 6 lines were passing through, and then when 4 lines were passing through, after this rotation no lines are passing through. So what can we say? We can say that the magnetic field lines linked with the coil, or in other words the magnetic flux linked with the coil, has become 0. Now since from the initial position from 6 magnetic field lines it has gone to 0, we can find that all the magnetic field lines are now passing outside the coil. So this means that the change in magnetic flux has been maximum, and thus the rate of change of magnetic flux is also maximum at this point. So since the rate of change of flux is maximum, what can we say? We have studied that induced EMF is directly proportional to the rate of change of magnetic flux, or in other words, if the rate of change of magnetic flux is more, then induced EMF will also be more. Thus we can say that at this point where the rate of change of magnetic flux is maximum, the induced EMF is also maximum, and as a result the induced current that flows in the external circuit is also maximum. Now notice what happens when the coil is further rotated in the clockwise direction. A point comes when the coil reaches this position again. Now over here, arm AB is on top and arm CD is at the bottom, unlike where we began from, where AB was at the bottom and CD was at the top. Now over here we have reached the initial configuration where the coil is perpendicular to the magnetic field lines. Now again in this case you find that it has reached the original point where all 6 magnetic field lines are passing through the coil. So magnetic flux linked with the coil is constant. That is, it becomes same as what it was initially. So no EMF is induced because there is no rate of change of magnetic flux. And since there is no EMF, no current flows. As you can see from the galvanometer needle, which is not deflected. Now this coil is further rotated in the clockwise direction. So now let's see what happens. Over here, when we are further rotating it clockwise, there is a change in the magnetic flux because from 6, now we find 4 are passing through. So there is a decrease in the magnetic flux linked with the coil. So an EMF will be induced, due to which current will flow through the conductor. Now let us use Fleming's right hand rule in order to find out the direction of current. We apply Fleming's right hand rule on arm DC. So my forefinger indicates the direction of magnetic field and my thumb indicates the direction of force. And if I stretch out my middle finger perpendicular to both my index and thumb, I will find that the direction of current is inwards, that is in this particular direction. Similarly, if I apply Fleming's right hand rule on arm BA, I will find that if I place my forefinger in the direction of magnetic field and the thumb in the direction of force, that is in this direction, then on stretching out my middle finger, I will get the direction of current as in the outward direction, as you can see. Now notice what happens in the external circuit. In the external circuit, the current flows and it reaches slip ring S1. Now the contact with S1 at B1 is over here and not over here. So current flows in this manner and all the way, as you can see from the arrows, in the external circuit. And the needle of the galvanometer is deflected to the other side. It flows all the way like this to brush B2 and then in this direction and through DC. So as you can see, in the external circuit, the current direction has reversed. Now again, when the coil attains this position, the rate of change of magnetic flux becomes maximum, as we previously saw. Now since no magnetic field lines pass through the coil, we can say that the magnetic flux linked with the coil has become 0. And if we compare this with the initial position where all 6 magnetic field lines were passing through, we can say that since the change is maximum, the rate of change of magnetic flux is also maximum. And under this situation, maximum current will flow through the circuit. Now since we keep rotating the coil, we attain this configuration again. Now again over here, as you can see, the coil has reached the initial position where all 6 magnetic field lines pass through the coil. So again we can say that magnetic flux linked with the coil becomes constant. So no EMF is induced and no current flows through the circuit. So in this manner we have completed one entire rotation in the clockwise direction of the coil. This produces an alternating EMF. As you saw in the external circuit, the direction of current changed in one rotation. So this produces an alternating EMF because there was an alternation in the direction of current. The EMF which changes its direction as well as its magnitude is known as alternating EMF. And this is the EMF that we got on rotating the coil. So now this EMF or the current that is produced in the circuit can be mapped on a graph. Now if we plot EMF versus the degree of rotation, we find that we are getting a sinusoidal curve. Now this degree of rotation needs a little bit of explanation that I am going to provide you right now. So firstly, we consider 0 degrees as the position from which we start off, and we rotate the coil in the clockwise direction. Now what happens when we rotate it in the clockwise direction? The magnetic flux linked with the coil decreases and a time comes when the rate of change of magnetic flux becomes maximum. At that point, the induced EMF will also be maximum. So on rotating the coil through 90 degrees, we obtain maximum induced EMF or maximum induced current. Now we keep on further rotating the coil. Now on further rotation, we tend to a configuration that was similar to the initial configuration. That is, all 6 magnetic field lines pass through the coil again. So we can say that since the same number of magnetic field lines are linked with the coil, the rate of change of magnetic flux is 0, and thus the induced EMF on turning it through 180 degrees is 0. Now the coil rotates further. Let us see what happens. We found that when it was further rotated, the direction of current in the external circuit was reversed. This was clear from the deflection of the galvanometer needle. So at this particular configuration, where no magnetic field lines are passing through the coil, we can say that since the change in magnetic flux has been maximum, the rate of change of magnetic flux is also maximum because the coil is rotating in a constant speed. Now notice what happens when the coil has been rotated through 270 degrees. Since there has been a reversal in the direction of current, we can say that the polarity of the EMF in the external circuit has also reversed, and at this point we get its maximum. So in the opposite direction, which we plot on the negative side of the y-axis, we get the maximum EMF. On further rotation, we go back to the original point where we had started off from. So again, the induced EMF becomes 0 because the magnetic field lines linked with the coil becomes constant. So in this manner, we find that we are able to generate a sinusoidal EMF in the external circuit. So this sinusoidal EMF will have a certain frequency associated with it. The frequency will be the cycles of the EMF completed in 1 second. And how is the frequency determined? The alternating EMF produced has the frequency that is equal to the frequency of rotation of the coil. Or in other words, if I say that the coil has been rotated 10 times in 1 second, it will mean that the frequency is equal to 10 Hertz. So we found that in this case, when we are rotating the coil, that is applying a mechanical energy on the coil, it is getting converted into electrical energy. And this was the principle that Faraday had used. And it is because of this that we are able to enjoy uninterrupted power supply during load sheddings and power cuts. So notice what happens when current reverses its direction while flowing. The current that is being produced reverses its direction in one rotation. Due to this, the magnitude also varies with time. As we saw, the magnitude that we obtain of the EMF and also the current is sinusoidal in nature. So not only is the direction changing, but the magnitude is also changing. This means that an alternating current or an AC is produced. This alternating current is produced by the generator, due to which it is also known as the AC generator. So the AC generator is responsible for producing alternating current, and this serves us during power cuts and load sheddings.